Welcome Junior Techies, this is Mr. Lodge, and today in our video we'll be looking at the particle model of matter. Now, a particle model is in fact a scientific theory which explains the behavior of matter based on particles. So what are particles? From our previous videos we know that particles are either atoms or molecules, where a molecule is more than one atom chemically joined to other atoms. Now, the particle model has got 4 key points. Let's have a quick look at them. The first point is that the particles themselves are tiny. They are so small that whether it's in a solid form or a liquid form, the matter, or in a gas form, we cannot see them. Secondly, these particles are all moving. In a solid, a liquid, and in a gas state, the particles are not at rest. The third point is that the particles are all surrounded by some empty space. By the term empty space, we mean nothing. Absolutely nothing. A vacuum. There is no matter in the space in between the particles of a gas or of a liquid or of a solid, as I'm showing with the yellow highlighter over here. These spaces are a vacuum. Then the last point is that there are strong forces of attraction in some cases between the particles and weak forces of attraction between the particles in other cases. But there are forces of attraction between the particles of matter. Let's turn our attention to the arrangement of the particles. In a solid, the particles are closely packed in a regular pattern as we see in the diagram over here. It is very easy to predict where the next layer of particles would be placed because of the regular pattern. One also sees that they are close to one another. In a liquid, they are still close to each other, but there is no pattern. This is an important point. There's no pattern. It's hard to predict exactly where the next liquid particle would be in this particle diagram. When we look at a gas, there's no particular arrangement at all. The particles are free to move at liberty and fill the space available to them. Let's turn our attention now to the movement of the particles. In a solid, the particles cannot move very far. They can just vibrate up against their neighbors. So they move back and forth and return to their original positions. In a liquid, the particles move quite fast and slide past one another, taking up new positions. They flow past one another, switching positions. In a gas, the particles are free to move very fast, taking up completely new positions without any hindrance from their neighbors. This corresponds to the particles' kinetic energy. Because in a solid the particles can only vibrate, their kinetic energy is low. Whereas in a liquid, the particles slide past one another, they have a medium kinetic energy. But in a gas, the particles can gain very high speeds and therefore have a high kinetic energy. Let's consider now the forces and the spaces between the particles. As we've seen, the solids are held together by very strong forces, and that relates to the fact that they have little spaces between them. The forces hold them very close. In a liquid, there are weaker forces between the particles, and they also have small spaces between them, but they are free to move around. A major distinction occurs with gases where there are extremely weak forces between the particles. And because the forces are weak, they have very large spaces between them, and that is seen in the particle diagram where they have large distances, and because of that, that relates to the weak forces in between them. Now, much of the research that has been done to support the particle model of matter has come from experiments on diffusion. Now, diffusion is the movement of particles from a high concentration to a low concentration completely spontaneously. Now, spontaneous means that this movement from a high concentration to a low concentration is done without any outside interference. If we look at the example over here, if we introduce some red dye molecules into a beaker of water, the water is shown by the blue substance with the little blue dots indicating the water molecules. The droplets of the red dye land in the beaker and very soon afterwards start to disperse. They start to spontaneously spread into the water, taking up as much of the water as they can until they are evenly diffused. At this point, they cannot get further apart from one another, and we say that equilibrium has been reached. Now, the rate at which this happens depends on whether it is a gas or a liquid. The diffusion happens faster in gases than in liquids, and it also is faster at a high temp compared to at a low temperature. So when it's hot compared to cold, you get faster rates of diffusion. The rate of diffusion is how quickly the particles move from the high concentration to the equilibrium position. Let us turn our attention now to changes of state. In order to change state, there has to be a change of energy. One needs to think about this. Energy either has to be gained by the material or it has to be lost in order for there to be a change of state. If we look at a solid and we consider how the solid becomes a liquid, the first process is that it needs to melt. So the solid melts and it becomes a liquid. And if it keeps on gaining energy, then the liquid will evaporate and form a vapor. So let's look at the particles, which I'm drawing in a fixed pattern here, all close together in the ice. When they gain energy, the particles are still close together, but they are free to move around one another, flow past one another, still closely packed though. And if we add more energy to the liquid, the particles now will move completely independently of one another, very far apart. So the little black speckles over there are now showing the water particles far apart, moving completely freely. In order for that process to have taken place, we needed heat energy to be taken from the environment. So we had to provide heat energy. In this case, heat was gained so that the phase could change, the state could change from a solid to a liquid to a gas or a vapor. Conversely, it's possible for energy to be given and released to the environment from the vapor. In this case, the vapor would release energy and in that way cool down. The vapor would then condense and form the liquid. Taking that one step further, if we release energy from the liquid into the surroundings, the liquid can freeze or solidify and form the solid state again. Junior Takis, thank you for your attention. Please look out for our next video on the density of matter. Thank you.